Okay, so we're in the midst of what I called quotients and twists. So let's let L be, recall that we're in the situation where we have T, G, Q, 6 module or representation with this ring of scalars R. And if L is not in sigma, I'm going to consider the characteristic polynomial that I considered before, but I'll put an L in it. PL of x is the determinant of 1 minus x times Frobenius. Well, before I was local, so I didn't have to put a subscript. I'll put a subscript now. Frobenius L, acting on our basic module T, and this is contained in R brackets x. Now remember that we had some supplementary conditions. For example, in our case, we want L minus 1 to kill our modules. We want our modules to be unramified, and of course they will be because L is not in sigma. And we want PL of 1 to be 0. So we force it. We force it in the following way. Let IL be the following sub-ideal in R, generated by just the amount that we need in order to force the issue. So generated by the integer L minus 1 and PL of 1. If we do such a thing and we deal not with the ring R, but we pass to the ring R mod IL and pass to the module T mod ILT, you'll notice that this module now satisfies all the conditions, the supplementary, all the conditions that we required locally. So I need notation for this. Let's let n be any square-free integer, positive integer, prime to sigma. So I want to produce an ideal which does the trick for n, so I'll let in be the ideal generated by all these ILs for L dividing n, this being an ideal in R. And when I play with the integer n, I'll be dividing by that ideal. So I'll be working in generally smaller and smaller rings as n gets larger. And I'll also, so that's what I mean by quotients. And I also will be twisting things. And for that, I need a kind of notation for a twisting module. So I'll call W my twisting module. W. N is equal to the tensor product of all the, well, how should I put it, FL stars for L dividing n. Now, this you should just forget about because it's a cyclic group. It's a cyclic group of order, of such an order that will kill all the modules. And so therefore, if I tensor things with Wn, that's just like twisting, and it's doing nothing at all. And by convention, I'll let W1 be Z. So the W's will represent the twist. OK. I'm ready to generalize the notion of Selmer group. And so if this is our basic Selmer group, I want to define what I'll call the nth satellite Selmer group for every square-free integer like that. How do you spell this thing? This is going to be called H of 1. And in general, I'm going to define something that I'll call h of n for any such n as on that board over there. For that, I have to give you a Selmer structure. So my Selmer structure, which I'll call Fn, which depends upon n, will have the following properties. It's a local condition. First, by sigma n, I'll mean sigma union the primes L, where L divides n. And by Fn, I'll mean the Selmer structure F if L does not divide n, the old Selmer structure. And at an L that divides n in sigma n, I'll mean the transverse local condition. Now, n consists in primes that were otherwise before unramified. And so, therefore, the local conditions were always the standard local conditions, the thing that I called h sub little f. What I'm doing is I'm sort of turning to the transverse at every one of these local conditions, replacing the unramified condition by a condition that's absolutely perpendicular, so to speak, to it. And I then can define h1 of Fn of Q with this new Selmer structure. I can do this only if I have the supplementary condition. So I can't do it for t, but I can do it for t modulo int, because in t modulo int I have my supplementary conditions, and I have to twist by wn. Now that I'll call h of n. And I have the same thing for h star of n, and I won't write that out too clearly, but it's, I replace Fn by Fn star. I replace this by the kernel of In and t by t star. Okay. Now, the jungle gym that I was talking about is going to be in terms of a graph. And so for that, perhaps I should remind you that if I have a simplicial complex, let's say C be a simplicial complex, which is going to be a graph in our case, a simplicial sheaf, and I don't mean semi-simplicial, I'll just call it a simplicial sheaf on C, will be a functor. So the functor will associate to every face, to every simplex of C. If it's a sheaf of groups, it'll be a group. If otherwise, it will be a sheaf in whatever category one is considering one's sheaf. And every time one has a face, you get a morphism. In particular, if gamma is a graph, you have the possibility of defining a simplicial sheaf on a graph. Okay, now I want to introduce my graphs. For that, I'm going to fix my sigma, and I'll fix a collection of primes, usually infinite, collection of primes, disjoint from sigma, and attached to this collection of primes, I'll just consider all square-free numbers I can build from this square-free product. Okay, fix the sigma and p, and then we'll have a gamma, which of course depends upon sigma and p. But where the vertices are just the elements of capital N, and the edges, well, if you have an N and an NL, both of them in N, you make a single edge between them, L being a prime, and I'll refer to that edge as E of NL. So you have a rather complicated graph. I mean, for example, there's one is a vertex, and if you have, say, 3 primes, you L and L prime, L double prime, you have L, L prime, L prime, L double prime. You have a whole box if you wish. You get a lot of circuits in this graph. Okay, I'm going to define on this graph something I'll call the Selmer sheaf. It'll be a simplicial sheaf as on this board. So the Selmer sheaf, as you might expect, is at vertex n, it's going to be the nth satellite Selmer group. And at any edge of the form ENL, it's going to be the local singular cohomology H1S QL T modulo INLT twisted. So I have to give you the attaching maps. The attaching maps go like this. So you have H of n, you have H of nl. Every time you have 2 vertices, therefore you have this edge between them. So you have H of e, and you have to define maps like that. Okay, so H of e is, of course, what I've just written down. And H of n is H Fn Q with coefficients in T mod In T tensor Wn. And H of NL is the same thing with F NL. Okay. Well, the first thing I do here is I restrict locally at L. Now, L doesn't divide N, so L is, the condition here is, the local condition at L for this Selmer group is that it be unramified. So this goes to H1F Q T mod INT, but I divide by INL, T, which is bigger, so therefore I can pass to the quotient, tensor Wn. But we can pass from here to there by what I call the finite singular map. QL, thank you. And in fact, in our situation, this is an isomorphism, and it's an isomorphism. It'll be, in applications, it'll be an isomorphism of free modules of rank 1 over R. Here, we simply restrict to L, and when we restrict to L, we get to the transverse condition. So we get H1 transverse QL T mod INLT tensor WNL. And by part 3 of our basic local proposition, we have an isomorphism from here to there. And so we just do it. So that is the the Selmer sheaf. And now I can define what I'll call a Kolyvagin system as a global section of this Selmer sheaf. So really, it depends upon what? I'll call it Ks of t from now on, but it depends upon, sigma, the Selmer structure, the set of primes, capital P, is the R module of global sections. Of the Selmer sheaf, which I'll call H over gamma. Okay, given this R module of global sections, we can have, there are various invariants. Perhaps the most telling invariant I'll just introduce at the moment is what I'll call the R module of L values. And that is, consider the homomorphisms of R modules, Ks of t, to the basic Selmer sheaf, which simply sends any global section to its value at the vertex 1. So L of t is the image. And as we'll see, or perhaps not, H1 over L of t is in good cases the module that completely controls the size of the dual Selmer group. In good cases. And we'll define good in a moment. There's also a possibility that this is 0. That is to say that the value of L, the special value of the L function, at least this cohomological L function, vanishes, in which case you can define an order of vanishing of these global sections, but I won't stop to do that perhaps until the end. I now want to specialize R and tell you the specifics of the theory of these special rings. So let's, instead of dealing with a general R, let's consider R a discrete valuation ring with finite a residue field of characteristic P. I'll call my discrete valuation ring D. So it's a DVR finite. Residue field, characteristic P. And the R's I'll be dealing with will be finite quotients of these, that is, say, quotients of finite length of these, d m to the d, and the little d will go to infinity. We'll adjust the little d. The P's I want to consider are the set of primes L, which are not in sigma, which have the property that the dimension of the quotient of t by the maximal ideal, I'll call that t bar, over Frobenius minus 1 times t bar is equal to 1. And also I want I sub L to be contained in m to the d for some d. Perhaps I'll call that p sub d. One of the beauties of the theory is that it doesn't much matter what p you take, as long as you take some p that contains a p sub d and that's contained in p sub 1. So most of the p's, the whole theory is completely robust in the sense that it doesn't matter whether you take, if you fix a d and you take such a d, and you can adjust. Okay. Now there are some theorems. There's some theorems, but for that I have to have a good situation where my t is good. And rather than, since I have limited time, I can give a list of very general, really, list of properties that enable one to make this theory work. And it's in my paper with Carl. But for our purposes, we can simply assume that the Galois group of Q in its action on the endomorphism ring over Fp, in the automorphism ring group over Fp of T bar is surjective. And P is greater than 3. That's enough, and there's far less we'll also do, but I'm going to assume this. Okay, now some theorems. The first I'll call the cross-isomorphism theorem. It says that there's a non-canonical isomorphism between these two things. Take n and m, any two vertices in capital N, that is, say, the vertices of our gamma. M is a bad letter, but I'll keep it. There is a non-canonical isomorphism between h of n plus h star of m. This is non-canonical. And h of m plus h star of m. This suggests a definition. A definition N is a core vertex of gamma, of our graph gamma, if one of these, h of n or h of n star, is 0. And we can produce a subgraph, which I'll call core of gamma, the graph generated by these core vertices. Now, there's a theorem about this subgraph of gamma. I'll call that the core theorem. Various parts to it, well, two. The first thing, and this is perhaps the most important, it's connected. Core gamma is connected. And it's also, I'll just say large for lack of time, meaning, for example, given any vertex m, there's a core vertex which is divisible by m. And there are other conditions which emphasize its largeness. The second is, if n is a core vertex, one of these is 0, but the way to say it, I guess, is, and then the other one is free. So I might say both h of n and h star of n are free over R. And not only, and the third is the statement that they're free of rank independent of the core vertex n. So that promotes the definition. This is now combinatorics, by the way. From now on, we're going to have a sort of rather strange collection of combinatorial features which will, I hope, emphasize the rigidity of these Kolyvagin systems. It promotes a definition of the core rank. And we have two of them, chi of t and chi of t star. One of them is 0. And these are the common ranks over R of h of n, h star of n, if n is core. One of these ranks is 0. Well, it gets a corollary. Let's suppose the core rank of t star is 0, which is in our applications perhaps the most used. The core rank of t star is 0, and you simply apply this cross isomorphism theorem, you get that for any h of n, any n, core or not, h of n is non-canonically isomorphic to a free module of rank that core rank plus a module that's isomorphic to h star of n. Why is that true? Well, you just let M be any core vertex and apply this cross isomorphism theorem, and you get that. So we have a sheaf here, a sheaf over an infinite graph with lots and lots of possible monodromy here, lots of circuits. And every vertex has the property that it has non-canonically a submodule of rank, a given rank, the core rank. Okay. Now, we can sort of try our hands at various possibilities, like chi of t is equal to 0. If chi of t is 0, it's completely trivial to prove that there are no global sections. Let us say ks of t is 0. There's no theory, so we're not interested in this. Chi of t is 1. When chi of t is 1, absolutely all of the classical applications come in this case. All classical applications occur here. So that's the case to application. That's the case to focus on. And the reason why that's the case to focus on is when chi of t is greater than 1, we don't understand the theory yet. This is sort of work in progress. We don't really, there's stuff to be understood here, but we don't really understand it. So we're going to focus for the rest of the hour on the case where the core rank is 1. Okay, that's going to be a hypothesis from now on. Now there's a structure theory when this core rank is 1. So here's the structure theory. So I'm supposing that the core rank of t star, of course, is 0 because one of them has to be 0, and then the core rank of t is 1. I should say in passage that this core rank is, in principle, easy to compute. If you use Euler characteristic arguments, you can relate it to the number of minus eigenvalues of complex conjugation and the fixed part of the decomposition group at QP on the module. And it's not. So you have to so you should think of this invariant as a fairly perspicuous invariant in the structure theory. It's not going to be a deep invariant. Okay. We have. Yeah.
What's the core rank?
What?
What's the core rank?
What is it?
Yes.
Oh, I defined it, right? And,
oh yeah. Okay.
What is the core rank? It's in this theorem, I claim that if n is a core vertex, then h of n and a star of n are all both free of a certain rank, and that rank is independent of the vertex. So I define that to be the core rank. And what I just said is that it's not a hard invariant to compute. Let us say there's a formula. The formula is something like this. It's the number. I'm assuming that chi of t star is 0. If chi of t star is 0, then it's the number of minus eigenvalues of complex conjugation in the Galois module T plus the dimension of the fixed part dimension of H0 QGQP. So for example, in the usual situation, we would assume that this is 0, in which case it's simply the number of minus eigenvalues of complex conjugation. That's what it turns out to be. Okay, I claim there's a structure theory for this Selmer sheaf in the case where the core rank is 1. Here's the structure theory. We have this Selmer sheaf, H over gamma, the Selmer sheaf. Of course, we can restrict it to the what I call the core of gamma. That is, say, the subgraph corresponding to core vertices. The first thing that one can prove about this is that this is a local system over core of gamma of free R modules of rank 1. That is to say, from what I said, over the vertices, these are free R modules of rank 1, but also over the edges, they are these local groups which are free of rank 1. And the attaching maps are isomorphisms in this situation. On the other hand, we can take a subgraph, which I like to call the stub of Selmer. And to give you a sense of what this stub is, there's this funny construction you can make with any finite abelian, well, not necessarily finite, abelian group. You take a cyclic subgroup of this abelian group. It'll have an index. Multiply that cyclic subgroup by its index. That'll be a subgroup of the cyclic subgroup, and therefore a subgroup of the group. Take the largest such group you can get. There's only one. Could be 0. And that I call the stub of the finite abelian group. Now, anybody working with Heegner points long enough will sort of recognize that really these Heegner points tend to live in stubs. Okay. What's the stub of Selmer? Well, I'm going to say it a little more concretely. So where should I do it? I'll do it here. In H of n, I define H prime of n to be the submodule of H of n given by taking the maximal ideal, raising it to the length of the dual, and multiplying it by H of n. I leave you to think this through, but you can see immediately, really, from what I have on the board, that these are cyclic R modules. And there's a similar, well, actually, one can just let H prime of any edge be equal to H of that edge, and one gets a sheaf, a subsheaf. If you restrict that subsheaf to the core, you get exactly the same H, because at a core vertex, this is 0, and by convention, maximal ideal to the 0 is 1. Okay, so here's a theorem, a structure theorem about this, which gives a kind of robustness to the definition of Kolyvagin system. The theorem is that the global sections of all three of these sheaves are the same. That gives us, if you wish, three definitions of Kolyvagin systems, but the most useful of them is that they are global sections of this local system of free rank R modules of rank 1 over this core, the core being a connected graph. The other aspect of this theorem is that every time you have a Kolyvagin system, let us say a collection of cohomology classes in every one of these satellite Selmer groups, which are compatible by the attaching maps, that collection of Kolyvagin systems in each of the Selmer groups perforce must live in the stubs. They're forced to live in the stubs. Okay? The thing is, I can tell you what happens when chi of t is bigger than 1. It's, here's the problem. I'll give you the problem in a nutshell. The answer is one wants to correctly augment the stalk of the sheaf over the edges. And that's delicate. That is to say, when chi of t is bigger than 1, you have too many Kolyvagin systems yet. Chi of t is bigger than 1. I think there are even sort of more rigid conditions that you can impose. So I like this theory when chi of t is 1. What was your question, actually? I didn't quite catch it.
This theorem.
Oh, everything from the rest of this talk on is under this hypothesis. Okay. Okay, well, that's interesting. I mean, so a Kolyvagin system is a section of such a local system over this core gamma. So the question is, how much monodromy does this local system have over this graph, which of course has incredibly many circuits? So we'll call this theorem 1. Theorem 2. And this is due to Ben Howard, who's a student of Carl's, and his proof is in an appendix in our preprint. There's no monodromy. Has no monodromy. This is trivial. I'll write it this way rather than saying that this local system is trivial, because this is the way he proves it. He considers circuits, and there are loads of circuits. And if you sort of study the situation sufficiently, it's a combinatorial sort of tour de force in a way. He simply shows it has no monodromy. Okay, this has corollaries. For example, corollary. In this situation, and now maybe I should repeat, that chi of t is 1, chi of t star is 0. What else? My ring is a discrete valuation ring divided by m to the d. Ks of t, let us say this collection of Kolyvagin systems is free of rank 1 over R. In other words, to put it in the context of a block diagram, you don't need Euler systems to produce Kolyvagin systems. You in fact have them. I mean, there they are, and there's a best one. In fact, we might call it a primitive Kolyvagin system is a generator. That's the definition of primitive. So you need a theorem about primitives, and here's the theorem. So it's the conditions of primitivity, if you wish. So these are equivalent. One. kappa is primitive. Two, kappa n, which of course always lies in the stub, not only in H, I called it H of n, is a generator of the cyclic R module H prime of the stub. For all n vertices, of course, again. Three, same thing is a generator of the cyclic R module for any one, for any n as such that H prime of n is non-zero. Four, and four doesn't follow from 1 and 3. Suppose I replace my R by the residue field, That is, say I let T bar be T tensored with the residue field. And so therefore I can talk about the reduction of kappa into Ks of T bar. 4 just says that kappa bar is non-zero. Now this is, by the way, a condition which is really a mod P condition. But it's a mod P condition in this combinatorial sort of jungle gym, but it's a mod P condition. And this is one of the things that attracted our attention. Because it does, in the Kato situation, give one a kind of mod P condition for the existence of a main conjecture. Sufficient condition, not necessary as it turns out. Okay. It also, this theorems 1, 2, and 3 simply tell us that we have Kolyvagin systems in all contexts, whether or not we have Euler systems. So perhaps we should go back to the block diagram at the beginning of the hour and sort of state theorem 4. If R is a discrete valuation ring, that is, say R, if I pass to the limit of all of R of d mod m to the d for all d, then H star of 1 is first. Perhaps I should have said that it still is true that Ks of t is free of rank 1 over R, and H star of t is functorially computable from a primitive Kolyvagin system. I don't know whether I have time actually to give this functorial construction, but I want to go back to the block diagram where we had at the beginning of the hour, at the beginning of the morning, I should say, we had L functions here. We had arithmetic here, where arithmetic means the cohomology of Selmer. We had the question of whether there's a connection between them, which is Birch-Swinett and Dyer, or perhaps if we're over the ring lambda, the main conjecture. We had what I called algebraic treasures. Which were directly connected by Gross-Zagier to L functions. We had Kolyvagin's marvelous method, which produced from these treasures Euler systems. And now we can consider these Kolyvagin systems. And there's a functorial control here of these Kolyvagin systems to arithmetic. And the whole issue of Birch-Swinnerton and Dyer or main conjecture, depending upon whether you're in one context or the other, then reverts to the issue of the connection between these two. One has, at least in the discrete valuation ring situation, Ks of t is rank 1. And the question is there an Euler system that gives rise to a primitive Kolyvagin system? So is this surjective? Now there are conjectures in Kolyvagin's papers which I think sort of somehow are sort of in that format. But what I wanted to do here was produce for you at least the definitions of a combinatorial sort of, let's say, refinement, or rather restriction, of the jungle gym of possible local systems, which sort of formalizes that a little better in the sense that if one has a surjection of the module of Euler systems to the module, the rank 1 module of Kolyvagin systems, that surjectivity is what you need in order to produce this passage. To the extent that you have it, you've controlled it, and to the extent that you haven't, you haven't. Now, one of the things that really interests me here at this moment is that what I've said is absolutely fine for discrete valuation rings. But when you get past to Iwasawa rings, you have exactly the same theory. These Kolyvagin systems are both rigid and they're also quite deformable. And so therefore you have a theory of Kolyvagin systems over Iwasawa's ring lambda. And the problem is, if you make this functorial construction on that, over the ring lambda, you don't quite get the arithmetic. You get something larger, and it's larger exactly as large as there are what are called exceptional zeros in the p-adic L function theory. And another thing that has sort of attracted our interest was that, in some sense, we would be able to understand the exceptional zeros purely on a cohomological level. Anyway, that's my introduction to the mechanism of Kolyvagin systems. And if anybody has any questions, I think I have 5 minutes. I have more. Yeah.
At some point in your lecture, you mentioned that R should be universal deformation ring.
Yeah.
So you could consider a situation where T is, would you have some specific situation in mind?
Oh, yeah. Well, the thing is that, in other words, do I have well, certainly I have a situation in mind where R is lambda. But what I would love to do is understand, on the one hand, I want to go to a slightly different context. What I would love to do is understand, on the one hand, the variation of the L function as one over modular forms, as one deforms them p-adically, sort of p-adic interpolation of L functions. Now we're beginning to have such a beautiful theory. This is sort of, the way I sort of like to package it, at least in the classical case, is there's a curve, which is called the eigencurve, where every point in the curve corresponds to a modular form of some sort, and it will have an L function, and these L functions will move along in a beautiful, rigid analytic way. I would like the Kolyvagin systems. I know that the Euler systems will not do this. You see, the Euler systems are integral in the sense that they have to do with these algebraic treasures, and they have a sort of integral weight, and they're discrete, and they're beautiful, but they don't interpolate that well. But the Kolyvagin systems have show every sign of interpolating well. And there's already a nice, we think, a nice theory over lambda, and I think we should be able to get a similar theory over sort of larger deformation rings, where what we call the slippage here over lambda, which I called the exceptional zeros, we call it in our paper, we're going to call it in our paper, the blind spots of Kolyvagin systems. That is to say, you can have a situation where a Kolyvagin system over a large ring, the whole ring of Kolyvagin systems, it doesn't map surjectively to the ring of Kolyvagin systems over the smaller ring. And that is going to explain to us the exceptional zeros in the p-adic L function. I want everything to interpolate, including the whole systems. Anyway, that's... Yeah? Yeah?
The exceptional zero is contained in my long paper.
Oh, great. So, I mean, you have a similar, you have a...
So, exceptional zero has something to do with what you call extended summer group.
Yes.
Which for me are...
Oh, sure, yeah.
my complexes, so you can see that it's exactly there.
No, I agree with you. So it's possible that what's happening is that the Kolyvagin systems are connected to your exceptional, your extended Selmer groups, right? I think that's what's happening. Yeah, thanks.